Thanks very much. First of all, I want to thank all the audiences for participating in our winter school and our special session about profiling attack. I'm very pleased to announce that one of the most well-known and one of the distinguished professors in this field is our guest lecturer. I think that her reputation she has enough reputation in this field that she does not need to be introduced. I am very pleased to announce that Professor Elisabeth Oswald from Klagenfurt University is our invited lecturer. And if I want to introduce her briefly, Elisabeth Oswald studied mathematics and information processing at the Graz University of Technology. She completed her PhD in the context of side channel attacks and application of algorithmic countermeasure in 2003. She started working at the University of Bristol as a lecturer in 2006. She has mostly known for her incredible and remarkable works in second-order attacks, template attacks, and attacking the masking schemes. Over the years, she has supervised many projects successfully in Europe and received many grants and awards, including ERC Constellator Grant and EPSRC Leadership Fellowship. Currently, she is a senior lecturer and full professor in cybersecurity at the University of Klagenfurt. And as you probably know, she is also one of the co-authors of the well-known book, Power Analysis Attacks Revealing the Secrets of Smart Cards, which has been cited more than 2,000 times by other researchers. And for me, it's a very great opportunity to talk to him directly. I am pretty sure that you are very interested in her talk. Elisabeth, we are very interested to listen to your lecture.
Thank you very much for the very kind introduction. The topic that I am speaking about today is one that I'm actually really passionate about. It's something that I've been interested in right from the start, right from my very earliest sort of attempts to attack devices up until now. And it's something hence that I've kind of authored quite a few things about over the years. And so I feel kind of this is a really fascinating topic, and I'm looking forward to hopefully getting you interested in this whole idea of profiling, of building statistical models for leakage that we are interested in exploiting. I hope that you can, I hope everything is coming through clearly. If you have any questions, or if at some point the connection is not so good, please make me aware straight away. Don't wait. Just use the chat functionality here and let me know if something isn't quite working on your end. So I have structured the time that we have into 3 parts. And at the end of each part, I have a little quiz, which I hope you will all participate in. And this also gives you an opportunity to ask something straight away. I've tried to kind of time things that we will have some time at the end, but my experience is with kind of these longer lectures that questions that you might have in the first 10 minutes are either easily forgotten by the end, or you can't quite remember anymore what you actually wanted to really ask. So I would really like to encourage you at the end of each part, when I have my little quiz, if there are any other questions, please post them into the chat so we can talk about these kind of questions straight away and don't kind of lose them somewhere. The 3 parts that I have as part of this lecture are sort of, the first part is a kind of a question about why do we actually profile? do we profile for only one reason, or are there different reasons why we might want to build a statistical model for the leakage of a device? This will bring us to the concept of different types of power models that some of you might have come across when reading through the literature. It also brings us to question what kind of measures should we be using to judge model quality, and what types of profiled models, what types of power models do we use for different purposes. In part 2, I then want to inquire in more detail about 2 or 3 specific techniques for profiling. Again, you should have come across these perhaps in the literature or by some previous talks, and I would just want to spend a little bit more time kind of comparing what will be classical templates and linear regression-based modeling. I will also always talk about a little bit about kind of classical machine learning techniques and deep learning techniques, but I have to balance time, so I'm trading this off for kind of overall kind of scope rather than going deeply down into each particular topic. And then in part 3, I want to talk about a specific instance of profiling where you are very much interested in portability of the resulting models. And that then sort of rounds off the kind of hour or hour and a half that I have designed here for you. So let's start off by sort of checking out what are actually the reasons for profiling. And I would like to get your answers or your views as well in this particular case. And what you can see here on this slide, and I might have to make your life a bit easier and copy the link that I would like you to visit into the chat. So let me do this very quickly. So I will type this link here into the chat. So profiling, in fact, is a concept that really dates back right to the kind of the paper that started everything off in our community, really, the differential power analysis paper by Kocher et al. And in that paper, of course, they present an attack strategy that we these days would call is a rather generic strategy. So I'm sure you know that they use a very simple t-test-based distinguisher and a power model where you attribute either 0 or 1 to an intermediate value that you're predicting. And this is kind of a useful thing, because if you only associate 0 or 1 to intermediates, then you don't make very many assumptions about the device that you're attacking. And now I'm curious about your opinion. What kind of assumptions do you think we are making in this classical Kocher attack, in this attack where we only use either a 0 or a 1 to model the power consumption of a device? I have a link here for you. I've posted the link into the chat. If you please click on that link and give me your opinion about what kind of assumptions do we make about the device when we use a 0 versus 1 power model. And I will actually load this page now to see what kind of views you have about this particular power model. So I will switch over to another tab if I can. Okay, so if you click on this link, you should get to this website and you can type your answer into the field that is called type your answer here. And what I would like you to think about and give me a response is, what assumptions do you make about the device with a 0 versus 1 power model? Maybe you make no assumption, maybe that's your opinion, and then just type no assumption whatsoever. Maybe you think there is an assumption being made, in which case type your answer in here. You can see you've got 20 characters. And if you press submit, then your answer will be immediately displayed here, basically. So please go for it, so we can kick off a little bit of a kind of discussion, really, at the start here. Okay, so I can see some people are doing this. So I always have to refresh this page. So I will do that regularly to see if any kind of views are coming in. Okay, so we've got three opinions. Now I think there are many people, so I expect to see a few more views here. Don't be shy. It's anonymous anyway. So I'll give this a minute and we'll see. So I can see some interesting responses coming through here. So one of them is, so we are interested in the differential power consumption. At least this is how I read the first response here. And you're right. So the assumption is that there is somewhere difference between, in this particular case, I guess this is what the next answer here means, at least one bit in the intermediate that is being predicted. Another response here says either works or idle. So either, I guess this means either something happens or nothing happens in the underlying hardware. And this really kind of governs the overall power consumption. Let's see if there's anything else coming, or if everybody agrees with what has been displayed here so far. And then I can also see the statement of the LSB, or what is the LSB of the target. So the assumption, I guess, that you mean by this is that indeed you kind of assume that the power consumption is somehow strongly related to the LSB of the target function. So I would agree with that. And it really isn't, so some people would say, well, you basically make no assumption with this kind of model, but this isn't quite the case. You make the assumption that a single bit, whichever one it is, I know in the Kocher attack, it often gets implemented that you kind of just select the least significant bits of your intermediate value of your target to predict the power consumption. But of course, it could be any of the bits that you are predicting from your target function. But there's the assumption that the power consumption is dependent on this one single bit somehow, plus perhaps that there are other contributions. So let me switch back to my slides. This takes a little bit seemingly. Okay, there we go. So the assumption, as I would see it, is that we kind of, in our model, we assume, so I've got here a slide which kind of introduces again the basic principle of a DPA attack, and I hope you're all familiar with this. So we have here the device that we are attacking, where we measure the actual power consumption from. And then we've got the model. This is really the thing that I'm talking about, mostly in my talk here. We've got this model, we have this assumption that we make about the working principle of the actual device that spits out predictions or hypothetical values, however you want to call these. And then we use a distinguisher here that brings these two things together, and then that allows us to make some judgment about which of the key guesses that we have also put into our model, which of these kind of indicate that this is the correct key. Now, our assumption here was that in our state, so what the kind of the reason why we are leaking on something, that in our state there is a bit that we are predicting which really strongly contributes to the power consumption, and the rest contributes as well, but we can be sure that there's this one single bit that we are attacking which makes a significant contribution to the power consumption. So one way of formalizing this is to sort of say our leakage on the state can be written as this particular bit that we have identified at leaks. I call it here as I, and that has a leakage contribution that we call beta I. And so our leakage on the state S can be written as beta I times Si plus something else that leaks on the state. And this is, in the Kocher paper, the beta I is simply 1. You don't really estimate that, but the first, perhaps the most naive way of profiling would be to ask, so how strong is the contribution of that single bit? And could we actually work out what our beta I is? So how strongly does it contribute? And you can do that by just using a very simple linear kind of regression style technique. Another thing here to bear in mind is that really this assumption here, it looks very innocuous, But in many processes, this mightn't hold at all. It might be that most leakage is determined by transitions from one state to another, which means that you wouldn't have an SI, but you would have an SI XORed with some previous state, which may or may not be known to the adversary. So we really make an assumption about the power model here already in this actually quite generic Kocher attack. Another thing perhaps to bear in mind when we kind of look at this super simple example is that if we have, so now that we've written down kind of our leakage model, our leakage assumption as well in this kind of slightly more mathematical manner, that the contribution that we are exploiting in this kind of attack, even if we would estimate the beta properly, so even if we actually compute this properly, well, because we are only estimating this kind of small contribution of the overall state, this is probably a really poor approximation of the overall power consumption. It's generic in the sense that it might apply to many devices, but it's not very efficient because it means we use a lot of traces in attacks with this kind of power model. And this already gives us a first kind of lesson really about models that we may use. Some of them, they are more suitable to be used across many devices, and others are very device specific. So this perhaps makes us already think a little bit about what is now really the purpose of profiling. Is it to make devices that are, or is it about making models that are super specific for a device, so that are kind of really good for attacking a particular device? Is it that we want to actually find out what leaks in a device so that they are good in terms of explaining the leakage? Or do we actually want to find out the leakage model of a device because we are interested whether or not a specific proof will apply for our implementation? And I shall again copy the link to this other answer garden into the chat box here, so you can tell me whether you believe profiling is about A, here, better for making models that are better for attacks, or B, explaining leakage, or C, fitting with a proof for an implementation. So let me find the link to make your life easy and copy paste this in. So in this particular answer garden, you don't need to worry about length or so. Just type A, B, or C, and then we will see how many people choose the different options and what your views are. And I will again have to switch the screen over to the website that I have open. So please type A, B, or C. You can do this multiple times. So if you actually think, no, this is A and B, then do A and then submit again for a B. That should work. So I'm again refreshing this website to see what your answers are. Maybe all, that's true. So then type A, B, and C. So what the answer garden thing here will do is it will enlarge the letter that gets more votes, basically. So we have a lot of people who like the answer that is B. I'm refreshing it a few times more to see if this impression here changes. It seems that you are, okay, C is now coming on. That's interesting. So please keep submitting. Okay. So we have a clear winner, which seems to be B, followed by C, followed by A. I'm going to switch back to this window here. So this seems to be our outcome. So this is actually fascinating. This is not what I expected at all. I'm curious, why did people choose B followed by C followed by A? If you don't mind typing your reasoning into the chat, I would love to see why this is. And I will also switch back in the meantime to my slides. So if you use the chat here, if you don't mind, and kind of if you have selected B or C or also A, just type in why do you think that this is kind of a good answer. Okay, so we've got one person saying, I think that A followed by B is the right answer. In my view, this would have been the more logical thing from my point of view to expect from students, because most people indeed, they build models because they want to improve attacks. But I find it fascinating that so many people said B and C. So I would really love if somebody said B. You know, I don't know you guys anyway, so in a way the chat is basically anonymous to me. To give me an indication of why you were so keen to use B or C. And I will then sort of explain my reasoning of what I would choose. Let's see if somebody else is daring enough. I realize it's a bit risky to kind of do that. B is the first step. Okay. See if somebody else dares. I won't wait forever, so then I will just sort of explain my reasoning for the answer. Okay. Right, so my expectation was that the vast majority of you, okay, in profiling, I think we prefer to find the leakage. Yes. It's more general than Koch's assumption. Okay. So I can see a few more people are kind of sharing their thoughts. Thank you ever so much. It makes it so much more interesting and fun, actually. So my expectation was that most of you would say, actually, we do that because we want to improve attacks, because this is really what the vast majority of research papers actually do. They take a device and they sort of ask the question, can we somehow improve over an attack that uses either the 0-1 model or a Hamming weight model? Can we do somehow better? The answer B is kind of also sensible. So I think there's also good reason why we use kind of modeling to kind of explain most of the leakage. But this has got, so this has clearly got an overlap with A. We hope that this would be better for attacks, but this is not necessarily the case. So if we include kind of sources of leakage into our model, that are actually very weak, then the impact of that on our distinguisher, on our attacks would be really minimal. But I would say it also requires a separate type of model building. So if you want to explain leakage very well, then you want to sort of know what variables in my state all contribute to leakage to. And if your state or if the device that you're working with is a 32-bit processor, then you will have a hard time testing all the many 32-bit variables that hang around. So this is indeed, B is a very sensible thing to try and achieve, but it requires probably a different approach to the classical templating that perhaps some of you will have heard of, and I will then talk about in more detail. And then also C makes sense. Also C is in fact a valid answer, because indeed, if you have a device and you want to run a masking scheme or whatever, and there is a proof of security for this masking scheme, then the proof will make assumptions about the leakage, and you should verify whether the device actually really corresponds to these proof assumptions. So you might want to use profiling to find out if the leakage model of the device truly corresponds to the leakage assumption in the proof. So the answer here to this question was that all three answers are correct, but most people really try and do A, and very few people try and do B and C. So that kind of leads me to my next slide, which is kind of really reflecting on, so what are the reasons, what are the contexts in which we want to use profiles? So attacks we've identified. In this particular case, we really want to find models that give us a very high prediction accuracy for new leakage. So if we kind of run the device again, maybe, I don't know, a week into the future, and we then run an attack, then we want that our model predictions still really accurately reflect the leakage that the device will actually give us. We also might want to use this in leakage simulators, which are somewhat related to proofs and leakage detection, where we want to also accurately predict the leakage of a device, but no longer of a specific device, but of a family of devices. So leakage models for simulators, they would be no longer one single device specific, but family specific. And then in proofs, we also seek to find kind of leakage models, but here we actually want to have models that work for more than just a family of devices across different architectures, perhaps even. So what you can see from this is that what kind of models we want to build depends on the application area, and we sometimes want to build models that are extremely device specific. Sometimes we would seek to build models which are maybe device family specific, and then we want to also sometimes build models that are much more generic than the two previous ones. So this brings me to these next three concepts: generic models, portable models, and really specific models. This is just now a different view of the previous slide. A generic model should apply to all sorts of devices of the same type. So to give you an example, a device that, or kind of devices that we often work with are from the ARM Cortex-M family. The M0 and the M3 devices, they're very similar in terms of their type. And what we are kind of then saying with a generic model, this would apply to any M0 or any M3 device, no matter who actually manufactured it. A portable device, a portable model, sorry, would apply to all M0 devices of one specific type, so of one specific manufacturer and one specific variation of an M0, for instance. And the specific model would only apply to the one M0 that we have in our experimental setup, in that one rig. So these are the different levels sort of between genericity and specificity. The reason why I'm emphasizing this so much is because models, so predictions that we make, you can classify them really elegantly by drawing on a well-known statistical concept called the Stevens levels of measurement. And this is about how well you approximate something. So a direct approximation of something, a direct approximation of the power consumption, would be something that, for instance, Bayesian templates and stochastic models give you, now specific to the side channel literature. And here the property of the model is that it really is as close as possible to the one specific set of measurements that you have. So you are approximating your true leakage on a ratio scale. The next level down would be to create models that are proportional approximations of the true leakage. So you can do this again via less granular linear regression techniques or stochastic models where you don't estimate the variance. That's the same thing then. It's also similar to using a weighted Hamming weight model, and you could use that in a correlation-based DPA. And here you're kind of having an approximation of the true leakage on what's called the interval scale. An ordinal approximation of the true leakage would be something where you only assign classes of leakage to intermediate values, and you can order them. So there's still a relationship between these classes. And then the least kind of demanding approximation would be called a nominal approximation. And here you really just assign labels to leakage classes. And there is no relationship between these classes on the labels. You can't order them anymore. And this is what we call often a fully generic DPA. And you use this typically in conjunction with what we call a partition-based distinguisher. And also mutual information with the ID model. This is exactly an example of using a nominal power model with a suitable distinguisher. So the slide here, and I think you will have to come back to this, there's a lot of information on that, associates types of models according to Stevens levels of measurements with DPA techniques. And a lot of people, in fact, really use kind of Bayesian style modeling or stochastic models. So this is linear regression plus the variance estimation to compute direct approximations of the power consumption of a device. And that means you've got a super specific model. It will apply to one device only. And if you choose to build different models, so going down here on the slide, the more generic your model becomes and the more applicable it becomes to also other devices across the family of devices or even across whole different architectures. And if these details are perhaps a bit too much, then maybe this slide is slightly more, I don't know, applicable to perhaps situations that you might find yourself in. So here I put together these different concepts that I've introduced you to on kind of a simple table that kind of lists different types of models, what their properties are, so whether they are good in explaining things or predicting things, and then what their typical use case would be. So a nominal model, so a model where you just assign labels to intermediates that kind of say, well, you will go in leakage class A and you will go in leakage class B. So they're really suitable to kind of think about whether certain proof assumptions work well for a device or not. And they're also super kind of portable. So you can use nominal models for proofs, for simulations, and for portable attacks. They have high explanatory power. They really tell you what exactly is leaking, but in terms of accurate prediction of the actual power consumption, they're pretty poor. If you then walk up sort of the ordinal models, there are not very many out there. So this is an unexplored area in our kind of community. They would be useful for simulation and for portable attacks. Proportional models are really good for portable attacks. They're not so good for simulations and they're really no good for proofs. And then direct approximations, direct models, they are really good for kind of simulating what I call here the worst case adversary. So the strongest attack that you can think of, but absolutely specific to a single individual device. So they're really high in predictive power, really low on explanatory power. So these are the kind of trade-offs that you can make. And so coming back to my question from before, why do you create models? Well, it really depends on what you're after. If you want to do worst case attacks, then you do direct models. If you're after simulations, you might be more interested in nominal models. And then you choose a very different style of model building. Maybe to kind of get this then to the kind of final step for the first part. We now have different types of models and their use cases, and to some extent, their different qualities. Now, how do we actually judge, for instance, the predictive power of a model? There are a range of statistical tools available for that, and the one that people would typically use is the R-square or cross-validation. And of course, in the context of side channels, we often use the key rank, the sub-key rank as a judgment. This means that we use this model in an attack context, and then because we are kind of now knowing the correct key value, we also know all the correct sub-key values. We kind of check after each attack. Where is the position of the true key in our kind of list of sub-keys after the attack? So our distinguisher gives us scores, and we can sort sub-keys according to the distinguisher score. So we've got a sorted list, and we can check where's our true key. For a good attack, we would expect that this is kind of on the top. For a not so good attack, we would expect that the true key is more at the bottom. So we can kind of do this, always check where is the key, what is the rank of the sub-key, and then kind of make a judgment about how good is our model based on how high is our key up in our list of ranked sub-keys. So this would be the typical DPA kind of style way of judging attack success. Explanatory power, we can largely judge by using an F-test, and the data complexity requirements are also important for model building. And this here you really have to essentially do by trying different models with different amounts of data and seeing how their predictive or explanatory power develops over increasing numbers of measurements that you put into the model. So I think this was probably quite a full-on first part. It was certainly not a gentle start. There might be a lot of concepts that you wouldn't have necessarily expected for a kind of a lecture on profiling, but I feel it's really important to put context into then doing maybe some Gaussian modeling. So I want to give us all a little bit of a chance to digest what I have said. So I have kind of 3 multiple choice questions now. And I will give you sort of 2 minutes or so at the most for each slide to look through it and to decide for yourself what you think the correct answers are. So there's a question, there are 5 answers, multiple of them can be correct. And just do it for yourself. I'm not asking you to share your answers or anything, just for yourself, jot down somewhere what you think the correct answers are. And then we'll go through and sort of look at that. And if you have questions, please use the chat so we can perhaps clarify some things straight away. So have a look at question 1, which is, when designing a profiled attack on a device for which you have an identical one in the same test harness available for profiling, would you consider using a proportional model, an ordinal model, the identity function as a model, a weighted Hamming weight model, or a model that explains the power consumption very well? Select all the answers that you believe to be correct. I will be moving on to the next slide in a moment. If this is too quick, please use the chat to kind of delay me. But if I don't see any, oh, no, this is too fast, I will just move on. Okay, question 2. A predictive model is a proportional approximation of the device leakage function, is good at helping pinpoint the sources of leakage, is bad for simulations, is able to predict the validity of proofs for a device, or is device specific. Again, select all the answers that you believe to be correct. I will be moving on to the next slide in a moment. Please use the chat if you're not ready. And question 3, a model that is meant for a target device that has the same architecture as the profiling device should be portable, be a direct approximation of the profiling device's leakage function, be based on a nominal model, consider trading of genericity and explanatory power, and be usable with a distinguisher such as correlation. Select all the answers that you believe to be correct. I hope you all had enough time to kind of consider your answers. So let's run through these questions and I'll give you my point of view. And I'll now just run sort of in the order of question 3, 2, and 1, just because question 3 is now displaying. So we have the situation that we have got a device that has the same architecture as the profiling device, but it may be from a different manufacturer. So it could be that I've got an M3 device from one manufacturer and then another device that says, okay, I'm also an ARM M3, but this is from a completely different manufacturer. So it could be that the implementations of the same architecture look really, really different. It could be that the devices are also in a different kind of package. It could be that they're integrated into some different kind of setting. So from my point of view, this would indicate that I want to have a model that is really portable, because I would not expect that a direct approximation of the power consumption of my profiling device would translate at all to any other device with the same architecture. So I would not choose a direct approximation at all. Should be based on a nominal model. Yeah, I mean that nominal models are very portable, so that I would say is a good choice. Consider trading off, and I'm missing an F here in my slide, trading off genericity and explanatory power. I would say so too, because we want it to be portable. It should be generic, really, and be usable with the distinguishers such as correlation. Well, I mean, that's a matter of taste, I would say. I would have no strong preference for that. If you kind of disagree with anything that I say, or if you find anything curious, then please do use the chat and post a question straight away or a remark, so we can pick up on this. But otherwise, I will go back to question 2, if I can. There we go. A predictive model is a proportional approximation of the device leakage function. Yeah, it probably is, because we are trying to be close to the actual leakage values. So we will need a proportional approximation. A nominal or ordinal is perhaps not good enough. A predictive model is good at helping pinpoint the sources of the leakage. No, not necessarily. And we will see later actually examples of models that are very good at predicting power, but that don't use all of the sources of leakage at all. So they're really bad at explaining power. A predictive model is bad for simulations? No, not necessarily. A simulation might also want to be close to a specific device, in which case a predictive model is an okay choice. But I would say you definitely want to trade off predictive and explanatory power in a model for a simulation. Is able to predict the validity of proofs for a device. It's very unlikely. We need explanatory models for that. And is device specific? Yes, most likely it is device specific. So I would agree with 5. And then coming back to question 1. When designing a profiled attack on a device for which you have an identical one in the same test harness available for profiling, would you consider using a proportional model? So if it's exactly the same type of device, again, from the same manufacturer, the same family, the same architecture and so on, and it's the same harness, then I would definitely try out a proportional model, because it might be just stable enough so it ports from one device to another. An ordinal model, but only if the proportional model fails. An identity function as a model, well, this is a nominal model, really, then. The identity function is like a nominal leakage model. Again, I would only use that if anything else fails. A weighted Hamming weight as a model. This is perhaps useful as a first step, because then you don't actually have to do any profiling. You just use a standard power model. And you maybe slightly adjust the weights based on what you see. And a model that explains the power consumption very well. Yeah, I mean, that's what I would be looking for, indeed. 5, I would agree with. So these would be my takes on these questions, stroke answers, or statements. And I hope that you can see that they enable you to reflect a little bit on the various concepts that I've introduced so far, and how to really apply them in some more or less real world contexts. So I'd like to pause here for a second and give you the chance to ask any questions that you might have right now, before I move on to part 2, where we look a little bit in more detail at the trade-offs that you can make between Bayesian templating and linear regression. For question 3, why did you say the nominal model is correct? So a model, here the scenario is that you have got two devices, they have the same architecture. So there might, for instance, be two M3 devices. So they have the same architecture, but they might not be from the same manufacturer. And they might not even be exactly the same type of M3. They might be in different packages, which means that a nominal model stands a chance to capture, what leaks, and this would be the same architecturally across different devices of the same kind of architecture family. So this could potentially work really well, whereas if you do a direct approximation, so a really predictive model, it's really unlikely that the power consumption that you have profiled from one M3 device from one manufacturer will have any meaning for the power consumption of an M3 from another manufacturer. And the same, of course, also applies to EM leakage. It makes no difference. I tend to use the word power consumption, but it also applies to EM, of course. I hope that makes sense. Okay. I don't see any other questions coming in, but I'll keep an eye on the chat. So let's move on. I want to cover a good few points here in the second part. And some of them I will kind of just run through at a good pace, because the actual details can be quite intricate and require a bit more time anyway than what we would have in our slot, even if I'd reorganize things. So I also refer you to the corresponding papers if you want to see the absolute minute detail. But what you will get from here is the kind of the conclusions that you can draw and a kind of a roadmap as to what you might want to actually do if you're in a practical situation where you want to profile. So I want to cover some classical methods for deriving predictive models. So this is classical templates and the regression-based templates. And I want to kind of explain to you what the differences are and what the similarities are. And then I want to very briefly focus on deep learning, and then we'll have another quiz. So predictive modeling, this is now what we are after. We are wanting to construct models for attack purposes. So we are interested in their predictive power. We want to build them such that if we get a device of the same type in the same setup, that we can predict this device's power consumption really well. We assume that we have perhaps a lot of training data available, but not infinitely much. So we are interested in whether or not a particular model building strategy requires more training data than another modeling strategy, and we will want to use a strategy that actually uses the least amount of training data overall. And we are also looking now at a situation where we are sort of in control as the adversary over, or the evaluator over, their kind of profiling device. This means that we can choose input steady device, we can control its randomness, and we can also set key material in the device. This often leads to a whole range of contention in the community. And the question is always asked, well, is this realistic? Who is actually doing this? And the very simple answer these days is that in common criteria-based evaluations, this is exactly what would happen. So there would be a profiling device. There would be a device that the evaluator can play around with. They can give the inputs. They can set the keys. And depending on the interfaces, they will also have access to randomness and control over randomness. This depends a bit on the device interface, but if it's possible, they will get this access. In evaluation regimes under the FIPS 140-3 kind of framework, no profiling happens ever. So let's just dive straight into the two kind of most commonly used approaches for predictive modeling. One we know in our community as classical templates. So this is by the paper by Chari et al., where essentially the headline is that you kind of say, well, my leakages, they all are approximately Gaussian in terms of their distribution, which means that we can estimate mean and variance, or mean vector and covariance matrix if we have kind of multi-dimensional leaks directly from the traces. And we get this by kind of grouping our traces according to some intermediate state that we pre-select. and then we kind of label traces according to some rule that we apply to our intermediate state. This might be that we use an identity mapping, so each intermediate value goes into its own class and hence becomes its own template. Or we might have a different rule where we say, well, we compute Hamming weights of the intermediates, and then we kind of build templates for those. And a completely analogous methodology is when we use what's called a linear regression-based template. So here we use a linear regression-based technique to kind of derive an equation that represents the power consumption. And we can do this, so the regression equation will then give you essentially an estimate for the mean value of the kind of modeled intermediate value. And we can then, alongside, estimate also a covariance matrix, like in the case of the classical templates. And you can actually, assuming that the points that you're including are reasonably independent, you can actually do all sorts of univariate approximations and then put them together. So you can kind of take advantage to some extent of independence assumptions when you do model building. But that's already sort of nitty-gritty detail, so I will not go further into this. Often in practice, we actually don't bother with the variances or covariances, in which case a lot of people would call this reduced templates. This is also the kind of the terminology that we then used in the DPA book, in case you're familiar with that. A lot of people would now sort of probably immediately want to ask, okay, so this is just statistics, that's a bit boring. What about machine learning and deep learning? What can we do there? And this kind of Gaussian modeling and linear regression, I mean, these are really classical machine learning techniques anyway. So if you look at this community, they will also be using these kind of approaches as a first step. There are more tools available then from machine learning in particular. And in particular, what in our community has been explored quite a lot are approaches around so-called clustering algorithms, supervised or not, so with training labels or without training labels. And they are interesting because they create models that are not direct approximations, but they are nominal or sometimes also ordinal approximations of the data. So they fit with other profiling goals extremely well, with portability, for instance. But they are not good tools to produce predictive models, really. And then, of course, there's the question about deep learning. Well, can we do more about if we use deep learning? And in our community, MLPs and CNNs have been investigated a lot recently. And I will actually have a few slides later on where I want to come back to this on a high level and explain to you what the findings are at the moment. But let's just go through the kind of techniques that we have available step by step. So when we do classical templates, then essentially what we do is we kind of group our measurements according to some labels that we assign to our intermediate values. And then in these groups of measurements, we then compute the mean or mean vector and variance or covariance matrix, depending on whether we choose to include just one trace point or many trace points. And this then simply gives us direct statistical approximations of the power consumption. So these are just the mean value, the mean and the variance just essentially get plugged directly into a Gaussian multivariate distribution. And there are all sorts of strategies of how the kind of the labeling of the intermediates work across different papers in our community. The kind of original paper really proposed that you would take pairs of key, and typically it's a kind of an input value to an S box or something like that, or plain text value related to the AES state or so. Which means that if you think about a case of an 8-bit intermediate state, if you have to do this for pairs of variables of this state, you have to kind of do quite a fair amount of templates. And this also means typically that you have to include quite a fair amount of data in your training set, because otherwise your statistical approximation of the mean and the variance is quite poor. A useful property to draw on to reduce this amount of training data is the so-called EIS property, equal images under different subkeys, that was introduced by Werner Schindler in his paper on stochastic models. This allows you to argue that actually we don't really have to build templates in many cases for pairs of input and key. We can just build templates for the output of the SBox, for instance, immediately, which reduces the amount of not just templates that you build, but also the amount of data that you need for a good approximation. I've mentioned the work by Schindler just a moment ago. So the other option that we use in our community is called, I call it linear regression-based templates. In his paper, Schindler et al. Called this stochastic models. And really, this is just a Germanism, basically. In Germany and in Austria, we often call statistics and statistics lectures, we actually call stochastic. So it's just another statistical model building technique. And here the idea is that the power consumption or the leakage function can be expressed as a polynomial in the intermediate value. So our power consumption y at point t can be written in this kind of functional form. So it's a sum of terms that depend on your intermediate x that are weighted somehow plus some noise term. And I know that this notation is not perhaps the most accessible. So if this kind of makes you slightly unhappy, then how about you look at my example down here at the bottom of the slide. So suppose your device is only a 2-bit device, and the state that it leaks on has hence only got 2 bits. Then the function that we would use to express the power consumption at a point in time on the state x would look like that. So you'd have a beta 0. This is the kind of the offset that you have maybe on your scope, plus a weight on the bit x0, plus a weight on the bit x1, and plus a weight on the interaction between x0 and x1. So that's beta 3 plus the noise term. And I hope from this you can infer that no matter how big your state is, you can always write down such an equation. And then what you do in your profiling is you're estimating those beta i's using your real data. And you do the same as in classical templating. You kind of split your data up into different kind of model classes. Often you do it by just kind of keeping each intermediate value in its own class. You kind of gather multiple power readings or leakage readings from it, and then you estimate the beta by just doing an ordinary least squares kind of computation. So this gives you then the beta, and with this you can describe the power consumption. And if alongside you also estimate your kind of your noise, so your covariances, then you have exactly the same as what templates would give you. And this is also a kind of a statistical fact. If you include all of these betas in your expression, and if you've got enough data, then the mean value that gets estimated via the linear regression will be converging to the mean value that you also get estimated via the direct average computation that you do in the Bayesian case. So there's a question here. Does it make sense to assume, oops, that's not gone. Oh, I saw a question coming in, but then it kind of disappeared. So sorry, I don't see it anymore. If you want to repost it, I'll try and look at it when it comes through again. Okay, so this is the explanation about that. Now, what are the differences? So when you build classical templates, because you're not really expressing your leakage function as a polynomial in many terms, you only have sort of the lumped together value in forms of the mean value. You have no chance of trading anything off. You always have to build, depending on your state size, 2 conditional mean vectors and 2 covariance matrices. In linear regression, you can actually say, well, I don't believe that these sort of higher order terms, so these interactions between the xi, that these would be contributing a lot because this doesn't correspond to any physical reality. So I'm going to drop those. And I'm only going to estimate coefficients for lower order terms, which means that you can adjust a little bit the complexity, and the number of terms that you include kind of also changes the trace requirements that you have. If you include fewer terms, you need fewer traces to estimate them well, which means that you could potentially more accurate models in fewer terms. So I can see this coming in again. Does it make sense to assume beta 1 is almost equal to beta 2? that's completely device specific. So for many devices, if you think about if the sort of low order beta i's correspond to the individual bits, then this would be the leakage that kind of corresponds to the Hamming weight component. And if what you are profiling, if the leakage mainly comes from the data bus, then yeah, these betas will be very, very similar, I would suspect. So if you want to save yourself some effort, then perhaps, but obviously you're trying to get an as accurate approximation as you can in this particular case that we're discussing. So you might as well actually try and estimate them properly. Okay, so how do we utilize these predictive models? Before I come to a comparison between linear regression and classical templating, well, you will either plug them directly into a kind of a Gaussian distribution and then use a log likelihood distinguisher, or you might also put them into a correlation, really. If you don't having any noise, for instance, then you might as well just use the mean value prediction of either modeling technique and just correlate it in with your data. That's entirely up to you. So the obvious question is, except for the ability to trade off certain things, what do we know about pros and cons of these two different approaches? And very early on, 2 papers appeared that made a really substantial analysis of these methods. One is called Templates versus Stochastic Models, and I give you here the full reference. And the key points that they find are the following: that if you build templates based on linear regression, then you typically can recover the key with fewer profiling traces. But if you have a lot of profiling traces, then often the classical templating achieves higher success rates. A slight drawback from this paper is that all of their conclusions are based on real-world experiments, which means you never know the true underlying distribution of the data. So it's unclear whether the kind of effects that are being observed are due to some estimation errors or whether these are true distributional differences that kind of impact on the trace complexity. And the scenarios that they tested were really favorable to linear regression. Another paper, again, I'll give you the full reference here, is called How to Compare Profiled Side Channel Attacks. That was a little bit later than the other paper. And here the idea was that perhaps we can use some information theoretic metric to quantify the model quality. And they actually also kind of stuck to scenarios where you would expect that linear regression would win out. So they confirm, in a way, many of the previous results. But what you can see from these 2 papers is that they kind of chose scenarios where you would expect that linear regression actually performs better. So a few years after that, we ran our own kind of study and tried to look at scenarios that would not a priori favor linear regression at all. And we were also interested to study in more detail the trade-offs that you can make by excluding coefficients. So in the 2 previous papers, the linear regression only ever kind of estimated betas for bits, but never for any interactions between bits. And we wanted to go a little bit further. So what we then kind of looked at, and this kind of graph here shows you the range of things that we studied, was we wanted to see what are the trade-offs between kind of having a fully defined model. So this corresponds to the original classical Gaussian templating kind of thing, according to Chari et al. And then some intermediate points down to the completely unprofiled Hamming weight model. And you can do this using linear regression. And as I said, we wanted to study this in a case where you're not just looking at the Hamming weight. We have this as a kind of prototype comparison, but we were really interested in cases where you have many nonlinear components of your leakage function, such that maybe you're really losing something if you do a too simplistic linear regression approach. And I don't want to show you all of the results, just a few which highlight perhaps some of the key findings and things that I think you should be aware of if you actually have to do profiling in practice. So what we see here are 3 graphs, where each graph corresponds to a different SNR in some now completely simulated results. And they are simulated based on computing the distinguishing scores based on theoretic distributions. This means that there's no estimation taking place. We compute this by completely specifying the underlying distributions. And what you should see here in these graphs is that the shape of the curves don't change. It's just that the number of measurements that you need to construct the model, that changes a lot. So the y-axis, the scale of the y-axis changes from the left-hand figure to the right-hand figure quite dramatically. And there are 2 graphs in each of these plots. There is a blue plot where we say we want that our resulting model has a very, very high quality. And the orange one says we want a resulting model that has good quality. And you can see that if we ask for good quality, we need much fewer traces than when we ask for really high model quality. And quality is model fit according to some statistical measure. The x-axis shows you the degree of the model. So this is how complex the terms are that we include. And the more terms we include, so the more we get to a kind of classical Bayesian Gaussian templating approach, according to Chari et al., the more data we need. And this is something that I think a lot of people are not aware of, who only build ever templates according to the Chari et al. Paper. That really, you need masses of data to have a really good model fit. But if you choose linear regression, you can slightly trade things off. And perhaps if you look at the graphs here, you would say, well, from about a degree 5 model onwards, I'm not gaining much of model fit. So maybe I shouldn't kind of include higher order terms, higher than 5, because what I gain by it, I need much less data. This is perhaps more practical in my situation. And when it comes to then experiments with really nonlinear leakage, so what we used is a kind of the leakage function that corresponds to the ASS box. So this is really among the worst case scenarios you could choose. And if you look again at model fit, then what you can see is that a degree 4 model is already a really good approximation model. Degree 5 model is a very good approximation, and then you don't win much anymore. So there is a kind of a sweet spot in the middle that you can trade off, where you can get a really high model accuracy, so super high predictive power, but for much fewer traces in your profiling stage. This picture here shows you, again, another view of that for our experiments with highly nonlinear leakage functions, where again, you can see that as soon as you have reached degree 4 models, you kind of capture as much of the power consumption as you really want to for really good attacks. So I want to summarize this. So what would you want to use then? So I would say linear regression is a really, really good alternative to the kind of classical profiling, especially when the true leakage function is simple. There's absolutely no reason to go for the sort of classical Gaussian templating. If you've got a really complex leakage function, you need to be a bit more careful, but certainly with the degree 4 or 5 approximation, if your leakage function has at most degree 8, then this is fine. From an attacker perspective, you can dramatically improve your predictive power and so your attack success by even just the tiniest bit of modeling. From an evaluator's perspective, you can lose quite a lot quite easily if you don't quite know what you're doing. So from an evaluator's perspective, perhaps stay with classical templating if you can, if you have enough data available. From an attacker's perspective, profiling really always pays off. This brings me to other approaches. So what about using deep learning? I promised I would say a little bit about that. So one of the really important things to bear in mind when it comes to deep learning is that this is not a kind of a miracle cure. It's not a miracle technique that suddenly will learn better and more and quicker than classical statistical techniques. And perhaps some things to bear in mind is that, for instance, can we actually learn such complex functions? Because really, we do have sometimes very complex leakage functions in the cases that we study. So the good news is that there is a theoretical result, which is called the universal approximation theorem. And this says that networks with 2 hidden layers and a suitable activation function can approximate any continuous function on a compact domain to any desired accuracy. So we have got continuous functions. This is what we typically get from our oscilloscopes. Compact domain, we have no gaps really in the kind of the domain that our function maps to. We are working over the reals. So this is also fine. So we should be able to construct networks that can capture the leakage function reasonably well. One thing to bear in mind is that all networks need to trade off the number of layers, so their depth, and the number of neurons per layer. And which trade-off you choose is completely unclear. Yeah. So if you thought, oh, in with regards to linear regression, so how do I know how many model terms I should include and what order should I drop? This question, in a way, appears again here. So here you have the question, okay, I have to configure now my network. How many layers do I choose? What activation function do I choose? And so on and so forth. It's the same style of question, but much, much harder to answer because you've got many, many more options to choose from. And as far as we know, we have no whatsoever clue, really, if we have a data set, what would be a good architecture for a deep net. Another thing to bear in mind is that perhaps you're asking, so what is the best approach to use? Should I always be using deep learning, or should I always be using linear regression, or should I always be using Bayesian templating? It's really important to bear in mind that there's another fundamental kind of insight in the machine learning community, which is called the no free lunch theorem for supervised learning. And what it really roughly says is that there is no best algorithm across the board. So there may be a best algorithm for your specific data set, yeah, but this is absolutely specific to a situation. You cannot expect that a, I don't know, CNN that you've configured that worked really well for one specific device or implementation on the device will be also really good for anything else. And the reason why this is kind of because any learning algorithm, and I now include into that Bayesian templating and linear regression, can only really learn the structure of the training data that it has seen. But our training data is never infinite. So we cannot guarantee that our approaches that we use will have seen absolutely everything that they could see. Because they haven't seen absolutely everything, if they encounter something new, really they have no clue about it. Hence, we cannot expect them to generalize to any unseen test data. Yeah, so this applies not just to deep learning, but also to everything else that is supervised machine learning. So don't really ask the question, what is the best technique? That doesn't really make any sense. But so what do we know now very specifically in terms of side channel stuff? What we do know from papers that have been published is that the two favorite things people have looked at are MLPs and CNNs. I consider a CNN is an MLP plus a convolution layer. And what we know is that MLPs, they train much more quickly than CNNs, and they also require much less memory. So if you're doing a kind of a DPA style attack, that mightn't really matter. But if you try anything multi-target, then this does matter, because holding many CNNs simultaneously somewhere in memory is actually really hard. And the computing power to train them is also quite enormous. The advantage of CNNs, though, is that because of their convolution layer, they can implicitly learn a misalignment in the data. However, we have also seen papers where they essentially say, okay, we know that the data is misaligned, so we align it first and then use an MLP, and that outperforms the CNN. Finding the best set of hyperparameters, so the best architecture for a network, is absolutely trial and error. I have not seen any kind of consistent advice given in papers, have not seen anything that worked well in one paper to really work well in another paper as well. So it's complete trial and error from my point of view. And also the papers find conflicting results, which again tells me that we really don't quite know how to configure things yet. And I'm saying this also based on some practical experience in my group. So we've also done a lot of deep learning over the last few years. And I would say making firm statements about something is a really hard thing. So my advice would be, if you have a device and you want to do profiling, start with some classical techniques first. If you know your traces are misaligned, go for conventional alignment techniques and try and understand what's going on. And if everything fails, then use a CNN by all means. And maybe you can learn from its convolution layer what you should have been doing. This brings me to the end of the second part. So I've got two more questions here, three more questions, I think. And to kind of be aware of time, what I want to do is I want to kind of now just run through them. And my third part is really quite short anyway. So question 4 that I have here is classical templates differ from linear regression-based models because they also include, also characterize the noise, include covariances rather than just variances, are less configurable, are based on the assumption that the leakage is Gaussian, and produce direct approximations instead of proportional approximations of the leakage. Select all the answers that you believe to be correct. So I give you a moment to make up your mind. So from my perspective, I would say classical templates don't differ from regression models because they also characterize noise. I can build regression models that characterize noise. So for me, one would not necessarily be true. They include covariances rather than just variances. Again, no, not really. You could characterize covariances if you wished in a regression-based approach. They are less configurable. That's true. From my perspective, this is a correct answer. They're based on the assumption that leakage is Gaussian. No, actually also linear regression assumes that the leakage is Gaussian. If you have leakage that is not Gaussian, then you should be using for non-parametric approximation methods, which I'm not discussing here. Produce direct approximations instead of proportional approximations of the leakage. Also not really. So as I said, linear regression, if you configure it fully and if you also estimate the noise, then this gives you equivalence to classical Gaussian templates. Question 5, templates, classical ones and linear regression-based ones, they can be plugged into a correlation-based distinguisher. Yeah, if you drop the noise, then this works. They are suitable for DPA-style attacks. Yeah, that also works. They must be used with a log likelihood distinguisher. No, you can, but you don't have to. They cannot approximate linear distributions very well. That's also not necessarily true. They can approximate it very well, but perhaps you could get a good approximation with less effort. And they're bit linear functions of the data. No, they are not. They can be complex functions of the data, but a lot of people, because they label intermediates by Hamming weights, they actually reduce the complexity of templates and linear regression-based models to bit linear models in that way. I'm keeping also an eye on the chat, just in case there are any questions appearing. And finally, deep learning-based profiling is provably more trace efficient than classical profiling methods. No, we haven't seen anything like that. Ensures portability of profiles. Also not really, no. It is completely not what we have seen so far. Requires careful tuning of the hyperparameters. This is correct. This is one of the crucial things, really. Cannot guarantee to produce profiles that outperform all other profiling methods on a device. Indeed, we have got no guarantee that it's actually better. It can be, but it doesn't have to be. And it fits into a general DPA-style attack framework. Yes, I mean, you can integrate nearly everything into a DPA-style attack framework. This brings me to the final part, and this is really quite quick, because so far I've talked about profiling that produces models that are basically a direct or proportional approximation of the power consumption, and this reduces portability. So if you actually need models that you can port from one device to another, or by device now means the same type from the same kind of manufacturer, but just a slightly different setup perhaps, then you perhaps stand the chance with some other really classical methods that are out there. But you slightly need to change tack in terms of your profiling strategy. And I thought I'd just really, really briefly kind of expose you to that. So we need now to kind of change tack in the sense that we are no longer looking for models that are direct approximations, but we go more for models that are kind of nominal or ordinal approximations. So how do you do that? So one thing would be that you kind of stop using supervised techniques, because in a supervised technique, you already make an assumption about the structure of your kind of leakage function. And perhaps you don't want to do that. So perhaps you're rather looking for kind of unsupervised techniques. And unsupervised techniques, they're largely based around what's called clustering algorithms. And they kind of learn themselves in a way what are important features in your data, dominant features. So things that you would expect survive or are the same between different devices of the same type. And there are some early works that explored that in the community, namely differential cluster analysis. And the other idea was this kind of idea of partition-based DPA attacks, where you use very kind of generic power models. And I give you here a kind of a listing of the, I would say, biggest papers that kind of do this kind of type of modeling. So mutual information fits into that. A KS test fits into that in terms of a distinguisher perspective, the variance ratio, and then it's multivariate kind of alter ego, which is called differential cluster analysis. And I would say at least you should have a read through the differential cluster analysis paper. I just want to give you a very brief kind of look at how this might work. So how do you get models from unsupervised clustering? So what you do is you take your traces and you kind of arrange them in a group, and then within these kind of, so you arrange them into groups. Typically this could be the intermediate value that you're interested in. It could also be based on the inputs. That's up to you. Then you compute what's called a pooled trace. This means that you average over all the traces which are in this group. This gives you now a kind of a data structure of traces. And then based on this kind of pooled data, you let a clustering algorithm loose. And this clustering algorithm will then tell you which intermediate sort of falls, or which input value falls into what cluster. And there are different clustering methods out there. It would go far beyond, you know, the time that we have to discuss them all. And there are also different kinds of similarity measures that one uses to then judge whether a specific clustering is good or bad. Again, this goes far beyond the time that we have. But there's a lot of choice out there, and people have investigated this in the side channel community. What works well is a kind of a k-means clustering, really. With a simple kind of silhouette index to judge how good clusters really are. So here's again the general strategy of how you come to these clusters. You partition your profiling traces according to something. Often it's the intermediate value that you are predicting, but it could also be something else. But key dependency is of course relevant here. And then you obtain a mapping by clustering the mean traces of each class that you have designed. And then you use this kind of clustering as a nominal power model in a partition-based DPA. I know this is a bit fast and you will have to kind of read through this in your own time. But what I want to show you is that this kind of strategy can work really well in terms of producing models that are portable and that are robust to distortions. And the paper that you could follow up on here is another one that I've co-authored with Caroline Witznall many years ago now, and it's called Robust Profiling for DPA Attacks. And what we study here is some clustering algorithms and DPA distinguishers to kind of see what kind of distortions can a model survive, can a nominal model survive. And maybe I just show you some pictures. I think that's more interesting than any further of these details. So what we, for instance, looked at was what happens if there's a difference between your profiling data set and your actual attack data set, where for some reason the traces are slightly kind of dislocated in time. This might be because you've got an unstable trigger, and the trigger might also kind of impact on the window that you're capturing per trace for analysis. And you can see this kind of idea here illustrated based on the two traces that I have displayed here on the top left. So you can see the traces look really identical, but it's the kind of the window that is selected for an attack is slightly different, perhaps to a jitter. And here in the table, you can then see this kind of trace distortion. We kind of implemented that based on some real data, based on a kind of a software AES and a hardware AES where we had some traces from, and we distorted them according to this rule. And then you can see how different types of portable attacks fare. So for instance, differential cluster analysis, a variance ratio, and the correlation-based DPA, where we do something to the traces to kind of make the models more portable. And surprisingly, most of the attacks actually work very, very well. So with minor modifications, so by using a little bit of unsupervised clustering, we can produce models that are portable, that can survive this kind of discrepancy. And I've got one other one, I think, here. Something where perhaps due to some setup issues, you have got a filtering that is slightly different. So you can see here in the two traces that I have on the slide on the top left, that the leakage happens roughly at the same time point, but it's kind of smoothed out in different ways. That's something that can happen quite easily with just minor setup differences. And again, we kind of simulated this distortion based on our real world data sets, and the distinguishers coped surprisingly well, I would say. So summarizing this, you can create portable models by using this kind of unsupervised clustering technique. And this is perhaps surprising to a lot of people, how much you can achieve by a fairly simple kind of setup, which is what we describe in our paper. And these proportional models, so these kind of models that we create, they have still some sort of proportional approximation as well, so they're reasonably good for attacks. And I would be really interested, so maybe some of you have an interest in doing this eventually, to compare these kind of techniques that we suggest to what actual CNNs can achieve. So at the moment, all the rage is, well, if you have misaligned traces, use the CNN. I would be curious to see what happens if you use some more conventional kind of portability techniques and compare that with the use of CNNs in the case of traces where you have some slight distortions. This kind of brings me to the end. I will leave you with the last two quiz questions. You will get my slides anyway. So I would say thank you to all of you for listening. Thanks to those who have felt able to post something into the chat and to kind of contribute to the answer garden things to make it a little bit more interactive. And at this point, I also, although she isn't here, I want to thank Caroline because of the many years of collaboration. We have managed to do quite a few amount of fun contributions in the area of profiling, and slides actually are in part due to her. This is the end of my talk. The rest of the slides, they just contain references, and you will get the slides as far as I know, so you can kind of follow this up. I will now just pay attention to the chat and ask, kind of try and answer any questions that are coming up there. So there we go. In case countermeasures are used in implementations, then is it possible to compare the success of different attack models? Yes, I mean, that would make a lot of sense, especially if countermeasures kind of perhaps change the shape of traces, so this portability thing. A comparison would definitely be sensible. If you are talking about countermeasures such as masking, then you also need to kind of change your profiling strategy accordingly, which means that you need to kind of create profiles for more than one intermediate value and then kind of consider how you bring them together to create joint distributions that are attackable again. I hope this answers the question. Okay. I'm keeping an eye if there's something else that appears in the chat. I don't see anything coming through. Oh, okay. There's a comment, location and scale invariants are already solved in image processing. Why should it be the case in side channels? So there's one methodology which we call elastic alignment. This has indeed been lifted over from, I don't think it was image processing, it was actually sound, because there you have got an evolution of a signal over time, which is a much better analogy than image processing to side channels. And yes, these things can work, but as with so many of these kind of learning techniques, they sometimes work better and sometimes they work not so well. So I've seen certainly cases where elastic alignment took ages to compute and didn't really improve anything. And obviously what convolutions that CNNs do, these are just filtering based. It's just basically applying several filters. And of course, if you can do this manually as well on your traces, it's just that as an attacker, you are confronted with a set of unknown, with a set of traces with unknown properties. So there's a lot of trial and error involved in getting it right. What is the ultimate, oh, hang on. What is the ultimate power of a profiling attack? I don't know what this means, to be honest. You mean, maybe you mean what is the best possible outcome or something like that. So depending on the device, of course, it depends on how much is leaked. Yeah, a profiled attack can only capture what is leaked. But if you have a simple device, like these old 8-bit microcontrollers, then with a profiled attack, if you extract lots of different intermediate values, including something from the key schedule, and this hasn't been masked, then a single trace will reveal everything that you want. So I guess the ultimate power is attacks with trace number 1. In image processing, when we find an image in different locations and also of different scale from the training one, I mean. Seems that it has nothing to say against 32-bit or 64-bit platforms. So you mean considering profiling on a 32-bit platform? Is that the question? And yes, if people want to unmute themselves, I think that's also fine. So profiling on a 32-bit platform, if you create the profiles for 8-bit intermediate values, like what you do for AES, then that's no problem. So we do that all the time. It's of course a very different ballgame if you're trying to compute a profile for the full 32-bit variable that you have available. So that you won't do with classical Bayes because you have no chance to trade anything off. When we do that, we use linear regression because we understand the power profiles or the kind of the characteristics of the devices that we work with very well. We know which terms to drop. So if you, for instance, consider our tools Elmo and Giles, which are leakage simulators for the M0 and the M3 platforms, these will give you these include profiles for 32-bit variables, and we do that by trading off things from which we know are not relevant. And I hope this answered the question. Okay, perhaps it did. So I'm still keeping an eye on the chat. If there are any other questions, now is a good time. And I guess it's up to the host to decide how long we kind of stay in the session. What is the current challenge in profiling? So, so I mean, there are different ones, right? So if it comes to pure predictive power, then I would say increasing the predictive power for native 32-bit implementations, that would be something that I would consider reasonably challenging. I would also say that going to more and more complex devices, because obviously the profiling depends on making an assumption about the state that you are kind of trying to include in your profile, and you need to find out that state, which again for more complex devices is difficult. And I think is one of you guys says, I think the profiling attacks face severe problems attacking heavily pipelined architectures. Indeed, because the state then includes many kind of variables that are from kind of before or after the instruction or the kind of the current state that we're trying to profile. So already for the M0 and for the M3, because you've got a 3-stage pipeline, models that you want to have a reasonably good predictive power, they need to be built on, if you do that, if you sort of think on an instruction level, if you profile a specific target instruction, then you actually need to kind of schedule this such that you have different instructions before and different instructions after, and your profiles depend on the variables, all the variables that are inputs to the 3 instructions in the sequence. So this is quite hefty to actually do. And if you go to even more pipelined architectures, you'll have to sort of see how to best trade off the huge complexity of the state and the predictive power that you're trying to achieve. And I would say there's a lot that can be done. So the efficiency is quite limited. No, actually, everything that we found for at least the M0, M3, and also M4 is that every little bit of profiling really helps. So I would say this, from an attacker's perspective, it always pays off. From an evaluator's perspective, you have to kind of put a lot of effort in to really capture the worst case adversary. So I think it's a slightly different perspective there. And then of course there's this whole issue of, you know, the many papers that use all sorts of deep learning approaches. And I would say, again, we don't know enough yet to really judge its impact. In particular, we find papers that say, well, this particular data set, this worked very well. And then the next paper says, oh, actually, I found something else. I think there's a lot of exploratory research going on at the moment, and that's probably necessary. And maybe 10 years down the line, we know better what should be the architecture if you're trying to learn intermediates from an 8-bit AES style implementation, and what should be the architecture if you're trying to learn intermediates from a 32-bit AES implementation. And does the architecture change if you're going to attack an ARX style cipher? So all of these questions are completely open and completely unexplored. Lots to do. What is the best countermeasure against profiling attacks? Is there any countermeasure? So all countermeasures have impact on profiling attacks in different ways. If you go for different hiding techniques, then this kind of means that even on a single device, you require models that are portable. So you then kind of shift the adversary to having to build nominal models, which means that they are not as effective, as trace efficient, I should say, as kind of proportional models. But then, of course, the same effect would also be on non-profiled attacks. And I would say the chances for a non-profiled attack to work in this context is nil, whereas with a profiled attack, you might still get an attack going. And then there are other countermeasures where you essentially create a much larger state by sharing out your intermediate variables. This means that an adversary, irrespective of whether they work in a profiled or non-profiled scenario, have in a sequential implementation many more individual items to profile. So this means you are increasing the effort really for an adversary. In a parallel implementation, you now have the sum of many shares leaking, and perhaps somewhere some joint distributions that shouldn't be leaking. So this again now requires different profiling strategies. And I would say countermeasures have, of course, an impact on non-profiled attacks, and they often make them extremely trace inefficient. And sometimes you can rescue that a little bit by a profiled attack. I hope that is kind of an answer that makes any sense to you. But if you ask me, what would be the best countermeasure, my standard answer, this is now irrespective of whether it's a profiled scenario or an unprofiled scenario, is never ever put all your eggs into one basket. You want to combine multiple countermeasures because this is how you probably get the most for the kind of money, for the amount of effort that you can afford. So I would always want to combine at least order 2 or 3 masking plus some hiding. Where are the power attacks going? I don't know what this means exactly, sorry. Do you ask for any research trends? Or do you mean that more in a practical kind of setting? Sorry, I need a bit of clarification to that last question. I don't quite know what you mean. Direction, yeah, so I'm not sure whether you mean sort of from a research perspective or from a practical perspective. I think from a researcher's perspective, I think we probably, I don't know, it's a good question. I think we want to put more effort into exploring how to make higher order attacks and multi-target attacks more efficient. So there's this technique called belief propagation that is perhaps not as well explored as it should be. I also think that inevitably we need to understand the impact of the deep learning techniques much better to really judge when we would like to switch to a deep learning approach and when we would just want to stick with classical machine learning techniques. From a kind of, excuse me, real world perspective, I would say again that the impact of deep learning is the one that we really need to understand better. And I also think that our ability to make trade-offs and to also when it comes to this whole RISC-V kind of effort that is going on, where we've got this kind of I would say this opportunity to impact on the instruction sets that are going to be defined. So there are lots of crypto hardware people contributing to the RISC-V effort and thinking about how should we actually define instruction sets that really benefit the computation of symmetric and asymmetric cryptography. So here also putting as a side channel perspective to it, that's also, I think, really important from the practical point of view. Of course, there's the whole post-quantum kind of business where we have implementations that are really different to anything we've seen before, and there's lots to investigate there. So this would be sort of things that spring immediately to my mind.
Okay, thanks very much for this instructive and informative talks. It was very interesting for me, and I'm sure that it was very interesting for the audiences as well. So I really, on behalf of the organizers and on behalf of myself, I really appreciate your very valuable talk and your time. Unfortunately, we have another session and we have to terminate the session, unfortunately.
I realize, yeah.
I hope to have you in our future actual or virtual sessions and virtual schools. I really appreciate your time, your effort, your very valuable talk. And if there anything else, unfortunately, I have to terminate the session.
No, I realize, yeah. Well, thank you for inviting me, and thanks to everybody who kind of has questions, because that makes it so much more fun for me.
Yes, there are a lot of things that I have to say, but I think that unfortunately, as you know, we don't have enough time.
Yeah.
So I prefer to send them privately.
Okay, fair enough. So thank you very much, and goodbye from my end.
Yes, goodbye. Goodbye, everybody, and thank you for joining us. Goodbye.